Okay, good morning. My name is Omid Mir, and I'm going to present practical delegatable anonymous credential from Equivalence class signature. This is a joint work with Daniel Slamani, Balthazar Bauer, and René Mayhofer. So let us start with the motivation. What is the identity? Digital identity, like your passport or driving license, are typically used for the authentication purpose. For example, whenever you want to buy alcohol, they might ask you to prove that you are over 21. So that's just a simple example. So we can implement this digital identity using the signature. Indeed, one authority can sign the attribute for the users. And users, and whoever has the verification key of this authority can verify this attribute. And this signature will act as a digital identity, or we call it a credential. So, however, this naive approach, has one big problem. The verification requires knowledge of all signed data or attributes. Even if you just want to prove single attribute like your age, you need to reveal all the other information as well, which is not good from the privacy-preserving point of view, right? So, anonymous credential is a cryptography protocol which can overcome this problem. It's worked as the following. So there's two steps in issuing. An authority will issue credential to users, which is a signature with a specific structure, algebraic structure. So very nice property. And in the second step, a user can now prove that using the zero knowledge proof and this credential, they can prove that they know credential for some set of the attribute without showing exactly the credential or additional information. And verifier does not learn anything beyond whatever user show, right? So even if this verifier interact with the authority, they cannot track the user activity. And it's provide really strong unlinkability, basically. We have a really nice building block for anonymous credential. For the signature, we can use the binary pairing signature like CL and BBS Plus. We use the commitment to hide the attribute and for blindly signed attributes. And for the zero knowledge component, we can use the Schnorr proofs, which is really efficient. And this component can work together smoothly and provide really efficient protocol. So delegatable anonymous credentials, I think it's clear from the name that we want to have like delegation property now. So this is because in the real world application, typically issuing a credential is in anonymous is an hierarchical structure. Indeed, we don't have one single authority. We have many authorities in between. So like one root authority delegates power to the intermediate authority, and that intermediate authority can issue the credential to the end user. So that's really typical scenario, real world application. So, but if I'm going to summarize the state of the art, so most of the existing approaches are not efficient enough for a practical use case. And if they are efficient, they don't provide all the requirements. So, for example, they don't provide attribute at all, or they don't provide strong anonymity. By strong anonymity, I mean anonymity during the delegation and also anonymity during showing credential. So we're going to address this problem. So before I jump to our scheme, I would like to introduce equivalence class signature. So in this type of the signature, the message is the vector of the group element in G. G is the algebraic group. So, and they try to partition this message space into the different equivalence classes. That's why they define like the equivalence relation. You can see it's a really simple relation, basically. If you have a vector m and m prime, there exists a random row that if you multiply a row to m, then you can receive like m prime. And if you think about it, m prime is kind of the randomized version of m. So with this relation, they can also now partition the message space into the different classes. So SPSEQ, or for short of equivalence class, I would say SPSEQ is now, say, instead of assigning a vector of the element, we're assigning a class of the message. So by assigning one representation of class. So to make it more clear, if you look at the picture, for example, so let's say UV is your message, is vector, and you have the sigma, which is the signature for this vector. I would say like now we have the random row that if you multiply with this vector, you receive the new vector. It's a randomized vector. So now if you this signature can adopt the signature to be valid for this new randomized vector. And if you keep doing this randomization, you have a bunch of the vectors which according to this class, they belong to the same, according to this relation, they belong to the same class, right? Because, and that's why they call it designing the class of message. So this is really important primitives in the privacy-preserving applications because provide unlinkability not only for signature but also for message. Okay, we extended this signature and proposed a new one, SPSEQUC, to be more fit with the delegatable anonymous credential. The first change is instead of assigning the vector of the message, we're assigning the vector of the commitment, set commitment. Still, all the elements are the group elements, but they are set commitment. What's the set commitment? So the set commitment looks like accumulator, that you can accumulate all the attributes into one single element C, and nobody will understand what's inside of the C until you open any subset value that you want. So for example, I can create the witness W to prove that birthday is inside of this commitment. This is called as set commitment. So these set commitment vector are completely compatible to SPSEQ message space. That's why we can also define the equivalence relation for this commitment vector. The second extension is that our signature allows you to extend this commitment vector by adding more set commitment into the vector. Again, if you look at the picture, let's say your vector is UV and you have the signature sigma for that. Now you can extend the vector by adding more elements like UVP. P is additional element, which is additional set commitment. And now you can adopt your signature to be valid for this extended vector, right? So, and you can also do this extension more regarding some upper bounding parameters. And I received the n dimension. So we defined new algorithms like change-rel that you can also do this functionality. You can just adopt your signature or extend your vector. So, but one important point here is that when you extend the vector, like you have a 2-dimension, now you have 3-dimension, this implies that you change the class as well. You change the class. This like 2 vector has different class and 3-dimension. So that's why in the paper we generalize this equivalence relation, and we define it as a family of equivalence relation, which means that regarding some fixed parameters, these classes belong to the same family of relation. So the last property that we add is that the signing process is tied to a specific user public key. Like if you want to verify a signature now, you need to also verify the user public key. Additionally, we defined another algorithm called it convert, which can switch a user public key to a new user public key. If you check the picture, let's say the PK yellow is the user public key, then you have a signature for that. And convert receive this signature, a new user public key, the green one, and it's able to convert and to switch this user public key. And the output, like this signature, is basically valid for this new user public key. This is important in application, basically. So from the privacy notation point of view, we like the SPSEQ standard one. We have also unlinkability for the message. We also have unlinkability for signature. So additionally, we have like 2 more privacy definition, revision and conversion privacy for our new functionality. So informally say that signature derived for extended vectors are indistinguishable from a freshly generated signature, right? That's really simple, informally. So, and same for the convert. Like if you switch the key, also you have the same property. So now we see that we can plug these new primitives to construct the delegatable anonymous credential. So it's easy, basically. Now it's just straightforward. You have the CA, is a root authority, we generate the root credential for a user in the first level, which is a signature for user public key in the first one, and a commitment vector, which all these commitment vector are including some attributes. And this would be a first credential. Now the user in the first level can delegate the credential to second user in second level by running our two new algorithms. Like first, change convert, so you run the convert and switch the public key to new user public key for the second user, and then run change rel to just add more attribute into the credential. It's like if you see C vector was C1, C2, and now in the second level you have the C1, C2, C3. C3 is the new set commitment, which is including new attribute. So finally, end user can simply now show this credential by randomizing the signature, randomizing the commitment vector, and also randomizing user public key. This is SPSEQ, structure preserving signature. You can also randomize all components, right? And simply create the witness that these set commitments are including some set of attributes, right? So I think additionally they need also to prove that their user public key are really they know the secret key belongs to the user public key. So, but that's really short proof and simple. So since all these components like signature and vector are randomizable, so we can hide the delegation chain easily because all components are randomizable and looks fresh elements. So, and one really nice property is like that no matter how many delegation have been done and no matter how many attribute has been added, right? So the final signature is a constant, like it has a constant, so it's a 4 element. So, yeah. Okay, if I'm going to summarize our work is that we propose like delegatable anonymous credential, which is efficient, simple, provides like strong anonymity and is attribute based. So we propose along the way a new signature, but not be interested in other application as well. We provide really precise security definition and proofs and models that you can check out the paper. Finally, we have like the implementations, and yeah, I just don't have time to explain too much details, but there's other cool things in the paper, please check. So thank you so much.
Okay, we have time for maybe a question or two while Tora sets up for the next talk. I don't see any questions on Zulip. Is there? All right, you have a question?
Thanks for the nice talk. Can you go back to slide 7, please?
Yeah.
So this extension that you mentioned that you can, like on the application level, essentially add more attributes about the user, exactly. Right? So what is required to do this? Adding an attribute, do you actually require the secret key for it, or?
A good point. So yes, in algorithms we have like the U key, like we call it as a delegation key or adopted key. With this key, you can do this delegation. You can add more commitments and attribute into your credential. Yes, you need that.
Okay, and this is going to go to the delegated CA.
No, your delegator has like the CA delegation key, and if you want to give you this power, it'll give you like this key.
Right, and is this tied to adding specific attributes only, or a specific relation?
No, it's just generic attributes. Whatever you want, you can add.
Okay,
basically.
Nice, thanks.
You're welcome.
All right. Okay, we have one more question.
Can you clarify this conversion procedure? Because it looked like a method to generate a valid signature for someone else's public key. And
Yes.
And that sounds dangerous.
Yeah, that's basically we define that because of the delegation need also to, the signature need to be transferred from the one user to the second user, right? So in this convert, basically what's do with that use the key that I said, like you have like specific secret value there that you can also change this. There is an additional component in the signature that you can adopt that component and add like the, like in the algebraic like structure, you can add like more secret key into the signature basically, and that secret key would be like the other user keys, right? So you can add to the credential, I mean to the signature. If I like understand your question, basically this convert will do like the switching the key, right? So
Okay,
there is one key and you can switch it.
Unfortunately, we have to kind of keep things moving to keep things on time, so maybe you
Okay.
can explain more afterwards. So let's thank Omid again.